Hello, everyone. Today, we'll be covering head loss, pipe system design, and pump sizing using Python. In industrial water distribution systems, a critical task for mechanical, civil, and process engineers is to design piping networks that accurately deliver water at the required pressure and flow rate. The efficiency and reliability of the system greatly depend on proper pipe sizing, accurate estimation of head losses, and correct pump selection. This lesson introduces students to the analytical process of determining major and minor head losses, calculating total dynamic head, and ultimately selecting the correct pump and motor for an industrial application. To reinforce understanding, we implement the calculations in Python, giving students an essential skill for modern engineering analysis and automation. The project example used in this lesson is a real-world scenario. Transporting water inside an industrial plant at a required flow rate of 50 cubic meters per hour through carbon steel pipes with various fittings and valves, students will learn not only which equations to use, but also how to structure input parameters and how to automate the design workflow. Major head loss. Major head loss represents the friction loss caused by water flowing along the internal surface of a pipe. It depends on pipe length, pipe diameter, pipe roughness, flow velocity, fluid viscosity, Reynolds number, friction factor. The governing equation is the Darcy-Weisbach equation, where F equals friction head loss, F equals friction factor, L equals pipe length, D equals pipe diameter, V equals flow velocity, G equals gravitational acceleration, 9.81 meters per square second. Minor head loss. Minor losses come from system disturbances such as elbows, valves, T's, contractions, expansions, check valves, filters or strainers. Minor loss is calculated using where K is the loss coefficient for each fitting. Total minor loss is the sum of all K values multiplied by the velocity head. Total dynamic head, TDH. The pump must overcome static elevation difference, major head loss, minor head loss, any discharge or suction pressure difference, pump power requirement. Once TDH is obtained, pump power is calculated, where ρ equals water density, Q equals flow rate, eta equals efficiencies. This produces the required motor size in kW. Input parameters required for a proper design. Before designing a system, engineers must know what information is needed. Input parameters are grouped into categories. Flow requirements. Required flow rate, cubic meter per hour. Fluid type water at standard industrial temperature. Fluid temperature affects viscosity. Pipeline geometry. Total pipe length meter. Pipe internal diameter in millimeter. Nominal size dN. Pipe roughness in millimeter. Material type carbon steel, SCH40. Elevation data. Static head difference between pump and discharge point. Suction tank conditions. Discharge pressure if into pressurized vessel. Minor loss components. Quantity of fittings. Long radius elbows. Gate valves. Check valves. T-branches. Sudden contractions or expansions. Pump characteristics. Pump efficiency. Motor efficiency. Water properties. For water at 20 degrees Celsius. Density equals 998 kilograms per cubic meter. Viscosity equals 1.002 times 10 to the power of -3 Pascal. These parameters allow the Python program to calculate complete system hydraulics. The input parameters have been systematically defined to support the development of a Python-based calculation tool. This tool will use the specified design data to accurately compute all required hydraulic outputs, including friction losses, minor losses, total dynamic head, TDH, and pump motor performance metrics. By establishing these parameters in a structured format, the Python program can reliably generate precise engineering results aligned with the system's design requirements. Project input parameters, summary description. The design of the industrial water piping system is based on a defined set of hydraulic and mechanical input parameters. These inputs are required to calculate friction losses, minor losses, total dynamic head, TDH, and the pump motor sizing necessary to meet the system's operational requirements. The primary project parameters are summarized below. 1. Flow rate, 50 cubic meters per hour. The system must deliver 50 cubic meters per hour of water, a typical industrial demand used in cooling, utility supply, and general plant processes. This value drives the fluid velocity, friction losses, and pump duty selection. 2. Pipe length, 120 meters. A total straight pipe length of 120 meters is used for head loss calculations. This represents the actual run of pipe excluding fittings. Longer pipelines increase friction losses and influence the required pump head. 3. Pipe diameter 100 millimeters, DN100. A DN100 pipe is selected to maintain appropriate flow velocity, 12.5 meters per second. Ensure manageable friction losses, allow compatibility with standardized fittings, and withstand typical industrial pressures. Diameter strongly affects Reynolds number and overall hydraulic performance. 4. Pipe roughness, 0.045 millimeters. A roughness value of 0.045 millimeters is used representative of carbon steel Schedule 40 pipe. Roughness directly affects friction factor calculations, turbulence intensity, and long-term performance as the pipe ages. 5. Elbows, 4 units. 4 long radius elbows are included in the piping layout. These fittings cause directional changes and turbulence, contributing to minor head loss through their associated loss coefficients K values. 6. Gate valves, 2 units. 2 fully open gate valves are present in the system. Though low loss when open, they still add measurable minor losses and must be included in the TDH calculation. 7. Check valve, 1 unit. 1 check valve is used for backflow prevention. Check valves typically generate higher minor losses due to turbulence created by their internal mechanisms. 8. T connection, 1 unit. A single T-fitting branch flow is included. Ts can introduce significant turbulence depending on configuration and carry relatively high K values, making them important in minor loss estimation. 9. Sudden contraction 1 unit. 1 sudden contraction occurs in the system, representing an abrupt reduction in pipe diameter. Such geometry changes create substantial turbulence and contribute considerably to minor losses. 10. Static head, 8 meters. The pump must overcome an 8-meter vertical elevation difference between suction and discharge points. Static head is independent of flow and forms the baseline head requirement for pump sizing. 11. Pump efficiency, 70%. A pump efficiency of 0.7 is assumed, typical for centrifugal pumps operating near their best efficiency point. Efficiency affects required pump power and overall energy consumption. 12. Motor efficiency, 90%. A motor efficiency of 0.9 is used, reflecting standard industrial electric motors, IEC, NEMA. Higher motor efficiency improves electrical to mechanical energy conversion and reduces operating cost. All of these parameters are incorporated into a Python-based calculation tool developed for this project. The program automates the hydraulic analysis, computes all major and minor losses, and generates final pump and motor sizing outputs with accuracy and consistency. By leveraging Python, the design process becomes faster, more transparent, and easier to validate. If you found this explanation helpful and you want more engineering tutorials, Python tools, and design walkthroughs, don't forget to like, comment, and subscribe to support the channel and stay updated with future content.